Okay, does everything make sense? Have you all started the assignment yet? Oh, okay, not yet. All right. Um, so if you don't have any specific place where you want me to focus, I'll just go very brief over the whole thing. All right. So before we start, this assignment is based on product design. We have to design a flange coupling to be able to withstand the forces that it will experience when it's working. So before we can do that, we have to start asking ourselves questions like, what are the types of forces that we will come across? So can you guys tell me some of the types of forces that we will be dealing with in this assignment? Stress and strain. Stress and strain aren't, they're the result of forces. So when a force is applied, you will have a stress and strain. But what are the types of forces that we can apply that will produce stress and strain? There are three general types. Torque is a product of force. So torque is force times distance. But I'm specifically asking for the types of forces. So yes, you're right. Torque will be the main cause of the force. Torque will produce the stresses. But what are the types of forces? Because torque is force times distance, yes? You know this from physics. Force times distance. What are the different types of forces that we will encounter? There are three types. First one being shear. Shear force. Then we have tensile force and compressive force. Now, understanding this and being able to identify the three different types of forces right before you even start the analysis is very useful, because then you can use your understanding to read data sheets. So a data sheet about a certain material, and it'll say its tensile strength, its shear strength, and its compressive strength. So if you're able to already understand what the types of forces, you'll know which bits of those information you need to use in your calculations. So if there's a tensile force being applied, you know you'll be looking at the tensile strength of the material. Likewise for shear and for compressive. Okay, so first identifying the types of forces is very important. So can anybody tell me the difference between, so tensile and compressive, when you have been doing physics, you usually call it normal stress. Or normal force, sorry. This is a normal force, tensile and compressive. Shear causes things to slide or slice. So if I give you a shape, let's say this cylinder, and I apply a force here and another force here, what type of force is this?
Tensile.
Yes, this is tensile. It's pulling the material. Pulling the material, and the force is perpendicular to the surface. So this is the element surface that we're interested in. And when the force is perpendicular, I mean 90 degrees to the surface, it's a tensile or compressive force. And in this case, if it's pulling, it's tensile. Likewise, if the arrow was going in the opposite direction, this would be a what type of force?
Compressive.
Compressive, yes. It's pushing the element. It's causing it to kind of squash. Now, what if we have a force like this?
Shear.
Yes, this is a shear force. Okay, if this was just part of another element, it will be causing this element to slice in half. It's like a knife cutting through something. This is a shear force, and the direction of the force is parallel to the surface. So this is the surface A, and the shear force is parallel to it. So those are the two fundamental differences between shear and tensile and compressive. Okay. So this assignment, you have to identify those forces even before you start your calculations. All right. Okay, question 2. How do we tell if our design is adequate? How do we know if our design is good enough, will be strong enough to withstand the forces that it's experiencing? How do we know? Any of you have any idea?
Should be above the working limit.
Sorry?
Should be above the working limit.
Should be able to yield.
All coefficients should be above the working limit.
Okay. Sorry, I can't really hear you. It's very muffled. So are you all familiar with this graph? The stress strain graph? Are you all familiar with this? Okay, brilliant. So if you're taking mechanical or you're taking civil, this graph is like your bread and butter. This is the fundamentals. This is like 1 + 2 for an engineer. All calculations should be about working limit. Yes, yes, that is true. And your working limit has to be below a certain value. Yes, your working limit has to be below the yield stress or the yielding limit.
Yes, sir.
This is our stress strain curve, and it's broken into 2 regions. What are these 2 regions called? What's the region 1? Any ideas what's region 1 called? This first region? This section. This is called the what?
Deformity, sir.
This is the elastic region. And then this is called the plastic region. Now what that means is when a material, so this is stress and strain, and as you apply a force, the stress will increase, and as the stress increases, so does your strain. In the elastic region, the stress and strain have a directly proportional relationship. So as we increase our force on the same area, the stress will increase and the strain will increase too. But then there is a certain limit. And at this point, stress and strain don't have a directly proportional relationship anymore. okay, the material starts to change its shape and it begins to deform. And when I say deform, it means when you take away that force, when you stop giving the force, say in this case, we took away this force, the material won't go back to its original shape. It'll have some kind of deformation. It'll either stretch a bit or go thin, and it won't go back to its original shape. And in engineering terms, this is called a failure. When the material or the part changes its shape permanently, this is called a failure. And we try and avoid any of our designs reaching that stage. And at the point, the last point on this elastic region, where our material will still be able to go back to its original shape, that is called the yield stress. And the yield stress is what we usually design all of our parts and models or components to. We always try and make sure that our working limit, like Jason said, our working limit is below our yield limit or our yield stress. So this is if this is our yield stress at this point, we're going to try and design our component to go to a maximum when it's working at this point, just so that it's safe. And the distance between these two, or the difference between these two, is called what? It's called a factor of safety. The factor of safety is a relationship between the yield stress and the working stress, or the yield limit and the working limit. So the factor of safety is yield over working. So if I told you that a part has a factor of safety of 1, what does that mean?
Less load is applied.
Yes, it means that our working limit is equal to our yield. Now, in reality and in engineering application, we never try and make our working limit equal to our yield. Why? Because there are always unpredictable things that can happen. Right? We might make a calculation for torque, but then there might be some kind of, I don't know, surge in power, or there might be impact or something along those lines, which might make the force a little bit higher and would cause our part to fail. So we never try and design it so precisely. We give it a certain factor. So these factors are usually 1.2, 1.3, and they can be anything up to about 10. 10 is usually the max, but it can go even more. Now, these different factors of safety are industry standards. So for different applications, different parts have different factors of safety. If you know the material very well and you know relatively accurately the kinds of forces that will be exerted, then we have a lower factor of safety. But if there are a lot of unknowns, a lot of unpredictable things that can happen, we have a higher factor of safety. So these kinds of things you have to keep in mind when you approach this assignment. Okay. Are there any questions just on this? This is just all background theory and background knowledge. Okay. So now we look at our assignment. Okay. So hopefully you've all read this already. You know what the deal is. The fact that the client is willing to purchase or produce 30,000 units per year lets us know that the client is investing a lot of money. And that is that's almost the problem statement for this assignment. the client is willing to invest so much money to make these parts. We have to make sure that it'll actually work. And there's no room for trial and error. There's no room for guesses. We have to be sure. So that is the reason why we have to do a calculation report. So in the task, design task overview, this is sort of like your design brief. And you are given things like the power that needs to be transmitted, the RPM or the revolutions, and your nominal shaft diameter. Now, using these bits of information, we calculate the torque. We do the torque analysis. Okay, so do you all understand load parts? So this part, let's call this part A, and this is part B. This part is rotating, and it has some kind of power, and it's rotating and causing a torque. It's rotating to transmit some power at some kind of RPM. Now we need to transfer this to shaft B. And the way that we do that is the forces have to travel from shaft A through a certain line to get to part B in order for it to move. So the critical load path, or the place where the most failure is most likely to happen, is along that path. And the path starts from shaft A, travels through the key. The key goes to the locking mechanism, which is the top of the hub. The hub then transfers that force through the flange to the bolt. The bolt transfers it through to the other side, and then it goes flange, hub, key, shaft, out the other side. That is the load path. And in the end, you should be having part B turning at the same torque. All right. So to do our torque analysis, we first have to define the relationship between torque and power. And that is a physics term. Power is equal to 2 pi n T over 60, where your n is RPM, power is in watts, and torque is in Newton meters. I won't go too in depth, but from the question, we are given n is equal to 25 revolutions per second. So what's 25 revolutions per second in revolutions per minute?
$1,500.
1,500. Yes, it's 25 revolutions per second multiplied by 60 seconds a minute. And we get our n. We substitute this in this equation, it becomes something like 2 pi 25 times 60 T over 60. And we can see that 60 and 60 would cancel out. So power is just 2 pi T 25 T. And making T the subject of the formula, we can find our torque. Because we know our power, the power is given in the question. We know our n, so this is how we would do the torque analysis. And this is always step one. You have to find out what exactly is the type of torque or the type of power that you're trying to transmit from one shaft to the other. All clear?
Yes, yes.
Yes.
All right, great. So the next analysis in the line is key analysis. Now, key analysis, what type of force are we dealing with? Remember, this shaft is turning this way. There is a force acting.
Yeah, for sure.
This is a shear force, yes. It is parallel to this surface. This surface here. parallel to that surface, so it is a shear force. Now, reading the question, we know the different types of keys that we can have depending on the shaft size. So our shaft size is 48. So this table says anything over 44 and including 50. So 48 falls in this bracket. We'll have a key width of 14 and a key thickness of 9 millimeters. What's the formula for stress? Either normal stress or shear stress. What is the formula?
Force divided by strain.
Force divided by area. Okay. So for all of these, you have to identify the type of stress that we'll be looking at. So you've already said shear force. So we're looking at shear stress. We have to find our force and our subsequent area. And the area will always be one of the terms that we're trying to find because we're basically trying to size everything. Okay, we're trying to size this key. We're trying to find out the total length of this key. That is the purpose of our key analysis. So to get your shear stress, you would then decide what is the material for this key. And the question already says that the material for the key is mild steel. And it has these features: 25 megapascals in tension, compression, and 28 in shear. So our shear stress in this case, it is a shear stress, so it'll be 28 megapascals times 10 to the power of 6 is equal to the force over the area. Now this area is what? This area, yes? And our dimensions are the width of the key multiplied by the length of the key. It's a rectangle. So width of the key multiplied by the length of the key, 28 megapascals is equal to the force over width of the key. We know from our data sheet as well. It says width of the key is 14. So we have 14 millimeters. And we need to find the length of the key. Now we're almost ready to start solving for this value, but first we have to identify our force. Now for this whole assignment, we're trying to transfer the torque. Basically, we're trying to transfer the power, from shaft A to shaft B, which means our torque has to be the same in shaft A and shaft B. So our torque is a constant. So once you do your torque analysis and you identify the torque that you need to transfer, the torque will be constant. And we've already said the torque is equal to force times distance. So if torque is constant, what's the relationship between force and distance?
Inversely proportional.
Inversely proportional. Yes, exactly. So as our force increases, our distance will decrease. And as our distance increases, our force will decrease. So you use this relationship and your value of D to find your force. D in this case is the shaft radius. So from the center of the shaft to halfway of our key, because half of our key will be inside the shaft, half will be used in the locking mechanism. Half of 9 is 4.5, so 4.5 is below here. 4.5 is above. And the center of the key is where we're assuming the force is going to be acting. And that happens to be on the shaft radius. So this is just shaft radius. Now, once you find your force, you can plug it back into this equation, make the length of the key the subject of the formula. You can solve for the length of the key. Now, if you come with a length of key coming out at, say, 52, let's say 50.8. Would you then take this as your length of key, or would you Round it off.
Round it up, sir.
Yes, very good. You'd round it off. Only reason being, if you were to give this dimension to a manufacturer, they'd probably swear at you because this is very, very precise. And even if you round it off to 51 millimeters, that's still very precise. Remember, they have to produce 30,000 of these. Oh, sorry, not 30,000, 3,000 of these units. Doing that at 51 millimeter intervals, very, very precise. So you would probably round it to either 55 or 60. Okay, so before we carry on, can anybody tell me what's stopping us from giving it a really high factor of safety? Why don't we just design everything to a factor of safety of 10? Why do we choose a factor of safety of 1.2 or 1.5? What's the reason behind that?
Intended load. Or intended load, maybe.
Yeah, basically. We don't design to such high factors of safety because that usually means we have to have a lot of material. We have to make things really, really big, really thick. And that can be a problem for two reasons. First reason, maybe it's supposed to fit in with other mechanisms and it can't take up that much space. Second reason, and the more likely reason is, it'll cost more. More material means more cost. And as a manufacturer or as a designer, you want to try and keep the costs down. So you try and find a sweet spot between cost effectiveness and safety. That is why we have industry standards and factors of safety. Okay, so if you were to choose 55, that would probably be a more logical choice than 60, because at 60, you would be making it almost, this is, what's that? That's 1/5 more than it needs to be. That's 20% more than it needs to be. This is 20% greater than what it actually needs to be. Whereas at this value, you're only 10% over. This is way too much material to be used. So that's why 55 is usually a more logical choice. But if you were to say in your calculation report, the assumptions that there might be some impact loading, you might say that this is actually a calculated factor of safety, a factor of safety of plus 20%. So we need this type of security. So that's why we've chosen a 60. No one or hardly any of you, any of the groups will have exactly the same answer. You'll all make different assumptions along the way. And this is one place where you can make a different assumption to anybody else, depending on the length of key that you choose when you round off. Just so long as it's always greater than the length of key that you calculate. All right. So that's the key analysis. Out of all the analysis, is there any one here that you're not quite sure about or one that you have a bit of issues with? Is there anyone that you're like not sure how it's done or why it's done that way? This Zoom meeting will end in about 3 minutes. So do you have any questions before the Zoom meeting ends? If you do, then I can start another session with the same login information and we can carry on for the next 20 minutes. It's up to you guys, whatever your... This is, after all, to help you guys with your assignment. And for those of you who haven't started yet, do you have any questions or any particular part that you're not quite sure how to do? Okay, so I'm going to end the session now, but I'm going to start another session straight away with the same login information. I'll discuss bolt analysis. Okay, so I'll just end this now and join me in the next session.
Okay, sure.